Okay, we should be back again for Evan of Code 2022 Day 18. The last 2 days have been very tricky days. If we take a look at the stats, I guess the last 3 days, what was day 15? Yeah, day 15 was a bit non-trivial, the part 2. Trying to figure out the optimization. We can see the clear spike in the ratio between how many people have actually attempted the problem and how many people are stuck on part 1 or... Yeah, so 3 tricky days in a row. We'll see if this is another tricky day or if we can let off on the gas a little bit. I do feel better today. My brain is a bit more here. I got to relax for the weekend and sleep in a bit, so my sleep is back to what it should be, even though I think there's some research about sleep debt and not being able to pay it back in those ways. But I do feel refreshed and ready to make a serious attempt at the leaderboard. So it looks like this picture is these were some like tents of some sort. This looks like a bigger tent with campfire coming out of it or something, or maybe this just is the campfire. So I don't know what these are, like scale wise. This is a lot bigger than these. But yeah, we'll see what happens. Make sure I don't knock my tea over. Count the number of sides. Okay. So if it's 1 1 1 1 or 2 1 1, they're touching because what, 2 other dimensions are the same, I guess? If their 2 dimensions are the same and one of them differs by one other, it's exposed, right? Okay, so I think it's something like that. So what do we want to do here? We just look at each of them and figure out all the faces. I guess. I guess we want to do it this way. then dx, dy, dz in deltas. We want to go through each other cube, and then if x plus dx, y plus dy, z plus dz is equal to d, then we will break, else is that right? Give me something to copy paste, please. That'd be 10. That's 64, so the real input, get this, okay. Wow, people are fast. Exterior surface area of the surface of air pockets. The cooling rate depends on exterior. Oh, I see. If it's an internal. Consider only cube size that could be reached by the water and steam. Interesting. What, so we only want to look at exterior? We don't want to look at interior points? How do we do that? So we only want to look at exterior faces. So how do we do that exactly? Is it actually a geometry problem? Do we have to compute like a convex hull based on these points? Seems like too much effort. I don't think it would be this. How do we think about this problem? I guess we can just sweep from... How big are these numbers? Oh, it's not that bad. Okay. So I think we just sweep across all of these. The exterior face is that, and if it's, yeah, okay. So if x, it'll be if min x is strictly like this. Oh. I guess that's not necessarily true. It has to be internal across along every dimension. Like, I don't think this gets us the right answer. But I think it might be something. Oh, it'll be so that's not quite right. It's probably on the right track now. It's like a little bit more nuance of that. It's like we sweep across the whole area, right? Okay, yeah. We have to do a sweep across for the pairwise combinations of x, y. So we draw that, and then we shoot out the ray on every, yeah. Okay. And then sweep. X, X, Y, Y, Z, Z. X, X, Y, Y, Z, Z should be fine. So, we find the ordering of the faces, and then if X, Y, Z is in pos, this should return us like one face. 1, 2, 3, 4, 5, 6, 7, 8. We get duplicate faces here. This is so hard to visualize. This is just a singular face. I thought it'd be like we can discount these faces because they're internal. And we just only pick the faces that are sandwiched. Oh wait, 1, 2, they're even. Oh god. Oh, people figured it out. Okay. Oh wait, no, these are the squares that... Oh, we walked through and we see what squares would exist internally, right? I see. So this is like the start, and then across each dimension, 1, 2, 3, 4. I mean, 225 is missing here. There's something special about it. I guess we just check all. Yeah, we do a similar thing where you can check. I see. If we check that location and the face that it would be touching has neighbors on all sides, we don't add in. We don't append it, right? Okay. I think it's just that, actually. So it's the same delta calculation. Definitely overcomplicated this. But cool problem, I guess. So in this case, we're internal. Otherwise we are, so we pass. Does this work? 64. I mean 225, right? Oh wait, no, this is deltas. And then we should be printing why are we only checking 4 deltas? Hello? Oh. Because we're terminating early. So when we're trying to place 225, we should, we have to make sure if they're all present, right? Okay, we're looking for 225. We see 1, 2, 3, 4, 5, 6. Yeah. One, two, three, 4, 5, 6. We should see all of them. Weird. Oh, I reset. Okay, it's 58. Oh, not quite right. I guess. How did people solve this one so quickly, though? That's my curiosity. This is going to be length of. Let's just see if this is any different. Wait, this is the length of the difference between the sets? Oh, I guess because those are cubes and then... These are faces. So what are we actually doing here? We're looking at every cube and then we're looking at its faces. So I guess you just draw a ray out to infinity, right? And if we never touch another cube, we're good? Oh, okay. I guess that's the logic. Trace out. I guess that's yeah. Oh, I mean that's kind of not strictly true either, but we might produce the right answer if we assume it's like a convex, totally enclosed thing, and there's no like open pockets. But we could try it. So we check the if nf in cubes, then we will internal, right? Internal faces. I don't understand. I mean, we already moved out by a delta, right? Wait, actually, if we see another cube here, that means we are internal, right? Uh-oh. So for some reason we're infinite looping here, which seems strange to me because the deltas are of course. And X and Y and Z. Okay. So we are definitely undershooting. We do see 225 as a possibility here. Is it one of those problems where we count how many cubes we see going through? Is it a geometry problem or is it just something very simple? Don't quite know. Like, why are these faces being detected? We're doing this once per face. Oh. Oh wait, no, yeah. No, we've broken out of the 4-1 queues. And then we try to ray trace out, continuing on backward. Oh, I guess we could be completely internal if... I see. So we're internal if... if we're surrounded on all sides, then we should nullify that face. Oh, wait. Maybe we can just fill ourselves in. You pick an arbitrary point in the middle. And you, okay, and you try to BFS to the edge. That's an interesting solution. You try to BFS basically out of the cube, and if you can't, then it's internal, so you fill yourself in, and then you rerun the cube algorithm. Okay, let's do that. I have no idea if that's the intended solution, but it would work. I guess we can just DFS that one, right? And then we can memorize if we can. Wow. Otherwise, return if and otherwise. So, if any of us can get outside, we become I wonder if this actually is the intended solution. I think it will work, but so let's see. If X and Y and Z. So they all have to be. If any of them are internal, then it becomes false, right? And then this back now. Oh wait, I'm not even checking. We don't go out that way if we're in the queue, right? Can we even do it this way? This isn't that big. So if we go off infinitely expanding, we're out of the picture. Let's just do a BFS. I can't. If we're outside, then we're false. And then we do the neighboring things. If this is, we don't add in touching another cube, otherwise horizon dot append. Right? And we return true if we get here. What is going on? Oh, I guess we only check. We check open. Okay, we just want to BFS on the open faces, right? Cause the okay, open face implies a cube. Okay, I see. Though I don't understand why. Why 225 isn't. Okay, it is giving is internal, but then like, oh wait, no, of course, the rest of these things will be external faces, I guess. I don't know. I feel like this logic should work. Like, these are obviously all ones that are on the outside, right? Because 0, 2, 2 comes from 1, 2, 2, and so it should expand off into infinity though. Oh, what is wrong with the logic? Why are we exploring ourselves many times? Like, this graph search seems to be allergic to exploring things outside. I don't understand why. It's not a typo, right? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Where's number 6? What's going on? 1, 2, 3. Oh. Wait, no, that's not it. What math is happening here? Oh. Wow, the dumbest bug. Two, 5 is true, yeah, so then we can just go and fill ourselves in, right? $58, yeah. What's lower over here? Oh, 2554. Wow. Huh, how did we do here? Whoops, I wanted this one. Okay, this should have been sort of obvious from the start, but we finished in under an hour at least. Woo! So I'm going to go jump to the present and explain this. Okay, I think we should be back now. We'll switch over to this. We are live again, and yeah. So part 2 definitely took a lot longer, probably, than it should have. But that's alright, we got there in the end, I suppose. Sorry, just gonna do a little bit more cleaning up here. We don't need any of this, and we don't need this. And the answer is just there. Okay, so all in all, this should have been a pretty straightforward problem. We don't need any of this. Let me just make sure that everything is cleaned up nicely. Cool. So the question is called boiling boulders. I failed to read a bunch of flavor text, so somehow there's elephants and we're in like near a volcano, even though the story started out with elves and Christmas for whatever reason. But essentially, in this problem today, we are given locations of a bunch of cubes of obsidian. Oh no, it might be forming obsidian. we're given the locations of lava droplets on a 3D grid. So we're given X, Y, Z positions, like so. And the goal of part 1 is to figure out how many sides are not being touched by another side. So obviously a cube has 6 sides or faces, and in this example, 1, 1, 2 and 2, 2, 1, if we visualize it, you can think of that as one cube directly next to another cube. And so because these two cubes are next to each other, their faces, one of their faces will be touching on each cube. And so rather than both these two cubes contributing 6 faces, resulting in 12 sides, because these two are touching, we only get 10 sides that are not touching another cube. In this example, it says the answer should be 64. So how do we solve this problem? Well, we read the problem input, straightforward enough. We've done enough input parsing in Advent of Code. I'll leave that as an exercise to the viewer. And ignoring this stuff, we can define these face offsets, or I might call it something different actually. Let's call it like offsets, like that. And this is the part that's relevant for part 1. So we can go through every cube and then pick a direction. So basically this cube 2, 2, 2 will have 6 different faces, and those faces will be occupying you know, where 1, 2, 2 should be, where 3, 2, 2 should be, where 2, 1, 2, 2, 3, 2, and 2, 2, 1, and 2, 2, 3. And the face is exposed if there isn't another cube, you know, touching in that location where the face should be. And so that's exactly what we do in code here. So we iterate through all of our cubes, and we pick each of the directions that we should be looking for another cube, which are basically -1 and +1 in each dimension. And then we go and check those locations against every other cube. I guess we don't strictly need to discount the other cube here, because we're just looking at offsets anyways, which will never be the cube that we're looking at. So we can simplify this a little bit more. Just make the code look a bit cleaner. We don't actually need these offsets here. So for other in cubes, like that, and we compute this new delta by basically, you know, adding that on. My point class, which usually I'd just be summing like these objects together, doesn't support 3 dimensions, so we have to write it out manually. If it's equal to, so we have to look through all the other cubes actually. Wait. Oh, we don't even need to do this. This is just really inefficient. All we really have to do here is just say, if we have to make sure the cube doesn't exist, right? So if nx, ny, and z not in cubes, then we continue on with the check. Let me just make sure that this still does the right thing. Like this. Cool. Yeah. All we have to do is make sure that the next location that we're checking for the cube on that direction's face is not in our list of cubes. And so ignore this part for now. This is for part 2. So if it isn't in the cubes, then great, we found an exposed face. And that's all there is to it. You just have to count them all up. It's a very straightforward solution. Now that I'm realizing how simple it is, and it makes sense that part 1 went so fast, I definitely overcomplicated it. So if we run that, we get 64 here for the sample, and running it on the real input, we get 4512, which is what's expected. So now for part 1, you have to consider that all of the cubes here might make like a big round shape that encloses, you know, another cube. Or like, it creates like a big, like convex object where there'll be faces inside that can't see sunlight, right? They're going to be like enclosed by this polygon, except instead of a two-dimensional polygon, it's a three-dimensional polygon. And so in this question, we only want to care about the exterior surface area of the droplet. We don't care about any faces that could be inside, right? And so I'm not sure if this was the easiest way to do it. It probably was, given the rate at which people were solving the question. But when looking at a potential face and trying to determine whether it's inside or outside, what you can do is just do a graph search from that location and try to get outside of the cube. If we can escape off into infinity with this graph search of checking, trying to walk to neighboring adjacent cubes and keep on doing that and doing that and doing that, if we can go off to infinity, that means we are not an exterior facing cube. We must be if you can go off to infinity, you are an external facing cube because you were able to escape. If you do the graph search and you can't escape to infinity, then you must be an internal face. So we'd write this. There might be a better way to do it, but I just am comfortable with writing a BFS. So this is very straightforward BFS where we start at a given XYZ, and we basically search. So, if we've seen it, we continue. If we get outside, so this is how we make sure we don't actually search into infinity. When we're reading the input, keep track of the bounds, the smallest and the greatest x. And if we ever are in our graph search get to something outside of the furthest cube XYZ, like minimum and maximum that we've seen, we know that if we kept going, we would go off into infinity. So if we see that, we're essentially off to infinity. So we should return false. We are not an internal cube. Otherwise, we try to add all of our neighbors, and conveniently, the same offsets that we're using to check different the faces on all 6 sides can be used to compute the adjacent 6 cubes to us. And so we do that computation and we check if we're in cubes. If we are, we don't add that into the horizon because we've touched another cube there, right? We're still, like, we shouldn't search any further. We got stopped basically by a wall. And yeah, so this is our BFS that will tell us if we were inside or outside. And so for part 2, all you have to do is check that if we're about to add a face to the answer, right? Maybe it reads better like this. And if we run this on the sample, we get 58. And if we run this on part 2, it's a little slow because we can probably improve that, and we could probably just do that together. But we get the correct answer here. So the problem here is that we're running like the BFS a lot. So what I think is like a convenient thing to do is known internals will be like this. And we can just have this be like this global object of things that we've seen and we know are internal, right? So at this point, add we are internal. So add everything we've seen to known internals. This should speed it up quite significantly. I guess let's try to quantify how much it speeds things up by. Let's try to time this. This is day 18. Okay. We run this, and it takes 2.82 seconds. So let's try doing it with this optimization. I know modifying global objects, bad, but this is advent of code. It's okay, don't do this normally. Mutating global state is confusing and hard to keep track of. So we want to add in everything that we've seen. And then here, if we're a known internal, we can just terminate early. If n in known internals return true. So let's see if this actually works. So much faster here. If we time it, we get a much faster answer. Basically, we're not repeating the BFS for every single node we've seen, because chances are in this input, there's like a big pocket on the inside, and we're doing this like big BFS through the internal pocket within this convex 3D gon, I guess, like over and over and over again. So by keeping track of what things we've already confirmed are internal, we can exit a lot earlier and not do these redundant searches over and over again. But yeah, anyways, turns out very simple part 1, kind of interesting part 2. I was getting scared and kind of overcomplicated the problem a bit probably, but I'm glad we had an easier problem, even if it did take quite a while for me to figure out part 2. It's a bit of a reprieve from the past 3 days. I wouldn't be surprised if already by tomorrow morning or something, this number here already like surpasses the past 2 days. Well, I don't know, at least the part 1 part. But yeah, that was day 18 for Advent of Code. Thank you for watching.